So today we are going to talk about the one of the most important linear data structure, that is queues. Okay, in the previous chapter we have seen uh, uh, the stack as the one of the linear data structure that we have studied, and we have seen its implementation, array based implementation, and we have seen some applications of stack, how stack is being applied to solve some different kinds of problems. Okay, so similarly we have another kind of linear data structure, that is queue. Okay, we have I have given an introduction in the previous class itself, in the first chapter itself, that what exactly a queue is. The name itself says here, the queue. Okay, something like, if you see this figure here, we have something like a line of students waiting to pay for their textbooks. Okay, it's a university library here, and library or a bookstore, whatever. Fine. So these are the students. They are waiting for to pay for their textbooks at a bookstore. Okay, like if you take an example of a supermarket as well, we have some list of customers, line of customers waiting to pay at the counter. Okay, so what do we have here? Basically it's the same as like an array, the linear structures. The elements are stored are in sequence here, but it has some kind of property. What is that property? The new elements are going to be added at the rear of the queue, and elements are removed from the opposite end, that is front of the queue. Get my point? Okay, what was that in the stack? It's a group of elements. It's a group of homogeneous elements in which the addition and deletion both were at the one end, called as the top of the stack. Okay, but the difference here in queue is what? The elements, it's also a ordered group of elements, homogeneous elements, in which new elements are added at one end, called as the rear or rear back, whatever you can say, from the back of the queue. Okay, and the elements are removed from the front end, from the other end, called as the front. Okay, so if you want to define a queue, you can define it as something like a data structure in which elements enter at one end and removed from the opposite end is called as a queue here. Get my point? You cannot hear Manzur. I guess he is having problem with his network. Is anybody having problem with my voice here? Good. All right. So basically, if you look at the behavior of this structure queue, so the element which was inserted first will be the element first out. Okay, so that is what a queue is, a first in first out structure. And what is the behavior of the stack? The element which is inserted last will be the first out structure. Okay, that is called LIFO structure. Unlike stacks, what is a queue? Queue is a first in first out structure. So that means, if you see this example here, if this person has come in here, okay, which person will enter out here? This will not enter out. This will be the element which was inserted first will be the first out. Okay, so this kind of structure is basically used in many kind of applications here. Okay, in the system applications, in the working of the operating system, we use this kind of queue structure. Okay, we will talk about that in detail about the applications of queues, where exactly this queue is going to be applied. Okay, hope everyone understood the definition here, the structure of a queue, how it looks like. Basically, it's a structured or ordered group of elements in which new elements are added at one end, called as the rear, and the elements are removed from the other opposite end, called as the front. Okay, get my point? So different textbooks have different terminologies here, like some textbooks call it as back of the queue. Okay, some textbooks says as a rear, so we will refer here as front and rear here in our coming sections, in the coming chapter. Okay, so now what could be the operations that we can perform on this structure? the same the same that we have applied in the stacks, that is constructing an empty queue here, initializing an empty queue. Okay, and we have an empty operation, check whether that queue is empty or not, and we can add one more operation here, full, to check whether the queue is full or not. Okay, and we have these two important operations. What is that? Adding an element and deleting an element. So if you are adding an element to the rear of the queue, we have this operation called as enqueue operation. Enqueue operation is what? It adds the element to the rear of the queue. What do we have? The operation on stack for adding an element. Anyone? What is the operation that we use to add an element into the stack? What do you call that? Push. Great. Push and pop are the two important operations in stack. To add an element is push, and delete an element is to pop an element from the stack. Okay, so similarly here in the queue, we have enqueue operation to add an element to the rear of the queue, and dequeue operation is to remove the elements from the front of the queue. Okay, understood? 5 basic operations that we can perform on queues. So we can add up here some more operations, like front operation, which retrieves the front value of the queue, and we can add the display operation to display all the elements in the queue. We will implement these operations in detail now. Okay, right. Okay, so now how we can implement this operations? Okay, basically we have two different representations, as I told you, array based representation and linked list based representation. So here we are going to talk about the array based implementation of queue. We have also seen an array based implementation of stack as well, right? So to implement this structure, as usual, we need an array, because queue is something like a list of homogeneous elements, or ordered group of homogeneous elements. To store these homogeneous group of elements, we need a structure called as the array. Okay, so for implementation of this queue structure, we need what? An array to store the elements of the queue. Get my point? Similarly, this structure was also used, array was also used to build a stack, right? Similarly, an array will be used here to build a queue, that is to store the elements of the queue. Okay, so apart from this array, we have two indexes here. One is front and the other one is rear here. So front is an index to track the front queue element. Okay, if you want to know the status of the front element in the queue, we track it using this front variable. And we have another variable called as rear, which tracks the last queue element position. Okay, since we have two ends here, the elements this structure has two ends, one is the front and the other one is the rear. Similarly, if you talk about the stack, we had only one end, that end is what we call it as top. Okay, so for building a stack we need an array and a top variable. Now here for building a queue we need an array to store the elements, that is we name that array as queue, and we need two variables, front and rear, to keep track of the front and last queue element positions respectively. Okay, now so for building this queue, for implementation of this queue, we have to to determine the front and rear positions of the queue elements. We have two kinds of approaches. Okay, that is fixed front design approach and floating front design approach. Fixed approach and floating front. So here fixed front means the value of the front will be fixed here. Okay, whereas in floating front the value of the front keeps changing as that of the queue. So let us see with an example here. Alright, see here, we have this queue. Okay, we will consider this queue after some NQ and DQ operations. Okay, suppose that we have 4 calls to NQ operation, yani we have NQ, call the NQ operation with arguments A, B, C and D. Okay, let us assume that if you NQ an operation, if you NQ an element into the queue, the value of the rear will be incremented by 1. Okay, suppose that we have called NQ with this argument A, NQ of A. That means what happened here, A has been stored into the 0 position, and assume that the value of front and rear will be 0 when the queue is empty. Okay, just like we had stack, if the stack is empty the value of the top will be -1. Okay, similarly if the stack queue is empty, when you initialize a queue, create an empty queue, what we do, we initialize the value of front and rear to 0 here. Clear my point? Okay, so when a element is being added here, okay, the element will be added at what position? At rear position. Get my point? Okay, so what is the value of rear here in the beginning? It was 0. So at 0 position A will be inserted. Clear? Next we called B, we called NQ with B. Now B will be inserted at 1 position because we incremented the value of rear by 1 here. So now rear is 1 here. Okay, and we called C, the value of rear was incremented to 2, so now C will be inserted at 2, and we called NQ with D here. Now the value of rear has been incremented to 3 and D was inserted at 3rd position. Get my point? Okay, note that we are not incrementing the value of front here. Okay, in this approach there is no changing of the front value here, so front remains as 0. Now if you want to dequeue the front element from the queue, to remove the first element we create a hole here. Now you see this element. Okay, now after this 4 NQ operations, if you want to dequeue an element, so which element will be deleted first? Of course the element which was inserted first will get deleted. Alright, so which was which is going to be deleted? Of course this A has to be get deleted. Now when this A is deleted, we are not changing the value of any front here, so front will be the same as 0 here, but it creates a empty space, that is a hole here. Okay, right? So to keep the front of the queue, now when you want to delete another element, what happens? You cannot make a space. Okay, so what happens here? Something like these elements should move forward. Okay, if you take up an example of the people that are standing in the queue in shopping mall. Okay, what happens here? When a person goes out, what the other persons do here? They will move forward, right? Did you get my point? See, these are the persons that are waiting here, A, B, C and D. Okay, now if the person A has completed its job, okay, so this will be out, this will come out, right? So when this comes out, this position will be occupied by B. Okay, it will come here. I'm sorry. This B will come here and C will come here and D will come here. So what happens here? We have to move all of the elements every time, right? Okay, so this kind of approach, what we call it as fixed front design approach. Now you see, when this A has been removed, what happened here? B has come to 0 position, C has come to 1 position and D has come to 2nd position. This is what we follow in the shopping mall. Every person, when a person comes out, the second person comes in the 1st position, the second person comes in the 1st position, the 3rd person will come into the 2nd, the 4th will come into the 3rd. Okay, but this kind of approach is something complicated, because every time we have to push the elements from one position to other position. Okay, so this kind of approach is not efficient for implementation, because this is going to create more load on the system. Get my point? Understood my point? With this design, the NQ operation is the same as push, okay, and DQ operation is complicated. Why? Because every time we have to move all of the elements when you DQ an element, okay, which increases the amount of work done. Yani this will create more load. Okay, so to overcome this design, we have to come up with another design. What is that another design? That is floating front design approach. Okay, so what happens here? We, in this kind of approach, when you want to add an element, the value of rear will be incremented. Okay, and if you want to DQ an element, the value of front will be incremented. Okay, suppose that, let us see here an example. Earlier this was the empty queue here, the value of front was 0 and the value of rear was 0. We called up this operation NQA. So what happened here? At the rear position 0, A has been inserted. Very clear, right? Next we called NQ of B. Okay, in this position what happens? The value of rear has become 1 here, and at this 1 position B has been inserted. And we called C, the value of rear has been incremented to 2 and it has been inserted over here. Alright, now if you call a DQ operation, what happens here? The value at front position gets deleted and the value of front will be incremented by 1. Get my point? So if value of front is incremented by 1 here, so what does it mean? Yani B is the front element now to be gets deleted. Yani this will be the first element which will come out first now. Get my point? Earlier what happened here? Front was at this position only and we had to push the elements to make it front, but now here what we are doing, we are just moving the front to this position now. Okay, earlier front was 0, now we moved front to make it as 1, so that it remains at the same position, and that will be considered as the front position. Now if you talk about that shopping mall supermarket example, what happens here is the people will not move forward here. The cashier will itself move to that person directly. Get my point? Understood? Are you people getting my point or not? With and this is now if I call any operation here NQ of some 40. So what happens in NQ operation? Simply the value of R at the R position, okay, this value will be inserted. Yani R is what now? It is 0. So this will be inserted over here as 40. This will be inserted as 40 over here. Alright. So suppose if I have another operation NQ as 50. Now after you insert this 40, the value of R will become what? It will move to 1. R will be 1. R is equals to here what? It is 1. Now what is the value of F? It will be same as 0. Alright. Now if I have 50, okay, so this 50 will be inserted at this R is equals to 1. Okay, and this R will move to 2 position. R is equals to 2. Okay, and again if I call NQ of some 30, so 30 will be inserted at this position, and R will become 2. Okay, so when you keep on inserting an elements, the value of R is moving here. Okay, moving means incrementing by 1. Okay, and if you call suppose DQ here, if you call DQ, what happens? It will delete the element which is inserted at first position. What happened? This element will get deleted. See, this element is going to be deleted. Alright, and in the fixed front approach, what happens here? The value of front will not be changed, it will remain at the same position. Now this is an example of a supermarket wherein this is the cashier. Get my point? This person is what? This person is the cashier. This person is the cashier. Alright, so now the value of F will remain 0 here. Now if one element is deleted, one person has come out here, so what happens in the shopping mall? The persons which are at this position will come here, 50 will come here, and 30 will come here like this. Okay, and they will create a space over here. So what happens here now? 50 will come here and 30 will come here, and this will get deleted. Yani this will have empty space here. Now the position will be what? Something like this. Not an issue. But if you have 100 elements here in the queue or more elements, then this operation, DQ operation, is going to be more complicated. Get my point? This DQ operation is going to be more complicated. Why? Every time when you DQ an element, the elements have to push forward, right? Every time, like if you delete this element, what happens here? This 30 will move to the first position, and the element which is at the second position will come out here. This will come out here. This will move here. This will move here, like this, if you have more elements in this queue. Okay, so this kind of approach is fixed front design approach, the same as the people waiting at the supermarket. Okay, but we have more problems in this operation. So what we are going to do here now, we are coming up with the floating front operation. What happens in floating front operation? When you delete an element here, the value of front will be incremented to 1. Yani F will be here. Okay, so that if you want to delete another element, here, DQ, what happens here? Which element is going to be deleted? The element which is at the front position is going to be deleted. So simply as that, 50 is going to be deleted. You don't have to move the elements that we had doing in floating front. Yani don't have to move 50 to here, 30 to 50 here. No. What we are doing? We are moving the front position here. The position itself is being moved to from 0 to 1. Yani the value of front will be incremented by 1. Okay. So if you take up that supermarket example, the cashier itself is coming to the position which is over here. The people are not moving here. The cashier is moving here. Understood? Okay. The value of front is moving here. So F will be 1 and F will be 2, something like that. If you keep on deleting the elements. Hope you understood this. Alright, we have another kind of drawback or disadvantage here. What is that? Let us say here the elements which we have inserted here, A, B, C, are being deleted. Okay, A, B and C has been deleted. Now more elements have been inserted here, that is J and K. So what is the value of front here? It will be 3 and rear will be 5. Let me take up this example here itself directly again. And let us say this is 0 and this is 1, this is 2, and this is 3, and this is 4. Suppose that we have a queue here which of maximum size as 5 elements. Okay, and the value of front we have as 0 and we have rear as 0. All right, so now if I call NQ of 40, okay, and then NQ of 20, then NQ of say 30, and then NQ of 80. something like this. Okay, so I call this 4 operations here. So what is going to be the value of rare? It's going to be something like 40 will be inserted here, okay, and 20 is going to be inserted here, and rare will become 1, all right, and 30 will be inserted here, and 80 will be inserted here. Okay, so what is the value of front? It will be same, no deletion, no deletion takes place here. Okay, so front will be same, but rare value has changed, it will be 3 here. All right, okay, now suppose that we called dq, okay. Now if I call dq here, what happens? The value of front will become, which value will be deleted first? This is going to be deleted first, so this is going to create some space here, and the value of front will become what? 1, and rear will become 3, right? Yes. Good. All right, so now if I say here something like, okay, I'm calling another time dq, here 20 will be deleted first, and value of front will become 2, okay. And if I call another time dq, 30 is going to be deleted and front will become 2, okay. So let me change this value here. Front is equals to 2 and rear is equals to 3, and so I'll use this eraser and delete this element, okay. After this dq, this 20 gets deleted, and after this dq, 30 gets deleted. And what is the value of rear now? It's 3 and front is 2. All right, so now if I call another time an NQ operation here, NQ of something like 90, okay. So what happens here? The value of front will become the same, it's going to be 2, and rear is going to be 3. No, sorry, here front is 3 here. Front is 3 and rear is 4. Okay. See, I'll go back here. Now here at this position we are at 0 position, right? Front is 0, okay. And if I call dq now, if I call dq, front will become, I'm going to directly change it from here itself. It will be now 1, okay, right? And now if I called dq again, dq, so okay, now this is going to be deleted, right? So now front is at 1, so now this is going to be deleted, and front is going to become what? 2. Front is going to become 2 after this dq operation. At first, after first dq operation, front was 1, okay, and after this operation front will become 2. Okay, again if I call d here, now front will become 3, and this element is going to be deleted. Is that clear? Okay, so now the value of front and rear is 3 now. Alright, so suppose if I call another NQ with something like 90 here, NQ with 90, now the rear value is going to be incremented to 4, incremented by 1, okay, and at this position this 90 is going to be inserted. Alright, again if I want to call NQ of something like 100, so what happens here? What happens here? Can we insert an element now? Because it has reached the maximum position, we cannot insert here. But even if we want to insert an element, we have the empty positions here, but we cannot insert the element even if we are having the empty position. Okay, so to overcome this kind of disadvantage, what we do is we come up with another variant of this queue, that is circular queue. What happens here? The value of rear is going to be moved to 0 position. Alright, so now after this rear, and rear is going to be what? It's not going to be 5. If it is 5, it has reached the maximum position, okay, and you cannot insert it. Now rear will not become 5, it will move to 0. Okay, so that is what rear will become, what? 0. Alright, so here in this case, now in the NQ operation, we are not simply incrementing the value of rear here. Rear is equals to rear plus 1. In fact, we are applying some modulo operation. Rear is equals to rear plus 1 modulus the size of the queue. Okay, we will talk about that in the implementation part, but remember that using this we make this rear as 0 here. You see, we had J and K, and if you want to insert a new element L, rear was becoming 5, but it's not possible. Okay, now to make it possible, we use it as a circular structure, wherein the element of circular queue and the location of front and rear for the following sequence of operations. Yani, what is going to be the value of front and rear after these operations? Okay, and you have to show the status here. Very simple concept, very simple numerical kind of numerical here, a problem which has been asked previously in the final exam. Okay, so right, and please note that the capacity of the queue is here what? It's 4. So it's going to be something like 0, 1, 2 and 3. See, this part is the solution. You will not be given this part. This part you have to write it. The one in red is the question. This will be given to you, and you have to write the value of front and rear and the status. Yani you have to draw the status of the queue. Getting the point, everyone? See, So now initially the value of front and back will be 0. All right, so now if I NQ an operation here with 20, what happens here? The value of rear will be incremented. I mean, at this rear position, the value will be inserted at 20, and the value of rear will be incremented by 1. Okay, so after this NQ of 30, it's going to be something like 0 and 1, and at this 1 position 30 is being inserted. Now after NQ of 50, this value of rear will become 2, and it will be inserted at 50, 0, 1 and 2. Alright, and at if you call this DQ operation, what happens here? The value of front will be incremented now. Earlier this was increasing. Now when you call DQ, this is going to increase. Okay, so 1 is going to be increased, and the element which is at the 0 position, the front position, is going to be deleted. Please note that the element which is not at 0 position is going to be deleted. That is not considered as the first front position. The value of front will determine the front element in the queue. It's either it's going to be at 0 or at 1, or it's going to be in the last position. Okay, so front was at 0, so at the 0 position, front position element will get deleted here. Okay, another time if I call NQ of 20 here, the value of rear is being incremented to no, this is a problem here. It's not going to be rear as 1. It's going to be 3 here. Okay, all right, and the value of NQ is going to be 0 here. There is a mistake here. Okay, it's going to be 3 here. Okay, and it's going to be 0 here. All right, so it's going to be 3 here, and the element which is at 20 over here, and then if I call another time 10, so the value of 3 will become 0, which is at the 10 will be inserted at 0 position here. Okay, so now that the queue is full here, when the value of front is 1 and the value of rear is 0. We will talk about this, how we are going to determine whether the queue is empty or whether the queue is full. Okay, in the coming classes we will talk about this in detail in the